greetings, Honors Physics students. Day 134, Honors Physics. Capacitance under quarantine due to coronavirus 2020. Unfortunately, we find ourselves in a tough situation here. We'll do the best we can. So we're going to talk about capacitance today and physical devices that are capacitors. Well, most capacitors, actual physical capacitors, look like little blue cans. I'll talk about that in a little bit. But this is a large one. Most of them are much smaller than this. This is out of an old tape deck. You can't even see it, but the whole thing here is almost as small as, well, it's probably smaller than this blue can, this capacitor. But there's about 10 capacitors on this circuit board, and it's got about 15 resistors, which we'll talk about next week. They're little brown things with red, colored stripes on them. We'll talk about that. Some of you maybe have seen these kinds of things if you open up. Even computers have these things. Any electronic device, basically, at least a large desktop computer, tape decks, anything like a TV, has some of these devices in them. There's other styles of capacitors. This was actually made a different way, but it's a different style. It's a large capacitor. All these are very, very large. They have a large capacity to store basically energy. So don't call them capacitors, right? They're capacitors, but some people mispronounce it. But a capacitor is an electrical energy storage device. The basic model is an oppositely charged parallel plates, metal plates. Okay. So there are other styles, but here's a little model I have of this using colored paper. So in this particular example here, I have the two. If you can see it too well, I have 5 sheets of paper. But I have 2 green sheets. The 2 green sheets would represent the capacitor itself. And they're similar to the parallel plates we've been talking about for electric fields the last few days, where you have 2 plates, like this is the example right here, where you have 2 parallel plates that create a uniform electric field between them. So if I take these two plates, they're paper, but make believe that they're metal, and they're separated by a given distance. And the way they keep them separated a lot of times is they put a piece of paper in between them, something that's an insulator. And later on in the notes, we'll call that a dielectric. And they can put different materials in there, but that's the most common material that they put in these cheap ones, a piece of paper in between those 2 plates. And then what they do, and this is the basic idea. And, oh, by the way, I have a couple of batteries here on a holder. And I'm going to just to show you that these work. I'm going to hook up this battery, these 2 batteries. Doesn't really matter how many batteries you have, but all right. So that's a simple circuit, which hopefully we'll be at least constructing virtually in the next few days. We'll see what happens here. But that's a basic circuit lighting up a light bulb, all right? But the batteries can sustain a flow of electrons through the wires that light up the light bulb. Now, what we're going to be doing is charging our capacitor, and we do that, one of the most direct ways with batteries. You can do it with other devices, but the batteries, which is what you'll be using in class if we get that far, is basically what they do is they have one wire connected to one of the plates, and once again, these plates are they're separated from each other by this insulator, and when you connect these 2 plates, you won't be able to see what happens, but when you connect the positive side of the battery to one plate, what it does, on the other side, the other end of the other wire is connected to the negative plate. What it does is the batteries, because they have chemicals in them, can take electrons from the positive plate. They take them off the positive plate, or what might have been empty, or it might have been neutral to start with, but now it takes electrons off this plate, makes this plate positive, and then it puts the electrons on the other plate, so the other plate's negative. Now, they don't really want to be there so you need an active energy source like the batteries to move those electrons over there. And then, so you charge that up, and you put this insulator between them. If you charge it up too much, all right, the electrons so much want to get back to the, and I'll disconnect this for a second, all right? They so much, now this is charged, because I just hooked this up to the battery, all right? So the electrons went off of this plate, and they went onto the other plate. But if you charge this up too much, you put too strong of batteries, higher voltage, potential difference, the electrons will burn through this paper, and then you've ruined your capacitor. So they have ratings that they can go only so high. This one I think is rated at 20 volts. Don't put more than 20 volts on this, otherwise it burns it out or ruins the capacitor. But bottom line is, what they do with capacitors is then they'll take like another couple pieces of paper to insulate the whole thing. So I call it the Big Mac model, all right? So you have 3 insulators. If you've ever had a Big Mac at McDonald's, it's like, when I was a kid, they said 2 all-beef patties, special sauce, lettuce, cheese, pickles, onions on a sesame seed bun. That was what the Big Mac was. There was a song that went with that. You don't need to know any of that. But so like the Big Mac, okay, the 2 pieces of green paper I have here, which would be metal, are like the 2 beef patties on a Big Mac. And then the white pieces of paper that I have here are like the 3 buns, because the Big Mac has 3 buns. It has the middle bun, top bun, bottom bun. And these things are usually a lot longer. The other model you can think of is like, this is like, you know, and I know toilet paper is in short supply right now, but this is like 5-ply toilet paper. I mean, you can't, I mean, this is like Charmin, this is Super Strength Charmin. This is like 5-ply. This is like good stuff. Really long. And what they do, so it's layered, 3 thin layers, really long, and they take and roll it up like a roll of toilet paper, okay? They roll up those layers, all right? And then they put them inside that can. So they put them inside that can, and then, I don't know if you can see it or not, but there's all capacitors have 2 connecting spots. So what you do then is once all that material's inside that can, and once again they're usually small, then you can connect it up to whatever voltage source you're using, in this case batteries. And when I connect it, you can't see anything happening, but just like the theoretical thought experiment we did a few minutes ago with the green paper, the batteries actively take electrons from the positive plate, the positive metal foil. It's usually like a foil that's, once again, curled up and separated by that paper, and puts the electrons on the other side. So I've just charged this capacitor. Now it's storing energy. So that's what I just did here, and that kind of shows you the picture right there. Then then you result in that electric field that we talked about, the problems we've been doing. And these plates have an area which we're going to talk about. But bottom line is, and you might not be able to see this, but once I disconnect this now there's energy stored in this capacitor. All right, there's a separation of charge. And I'm going to do this, and you have to watch kind of closely. I don't know if it's going to show up too well in the video. But I'm going to now connect and make a circuit. Now I'm no longer using the batteries. I have my capacitor charged. And if I touch this other side, what it allows to do, because the wires are things that electrons like to go through. They won't go through that paper because the paper's an insulator, but I have copper wires here with a completed circuit will allow the electrons to go back home and then discharge the capacitor. So and it doesn't take very long. It takes about less than a second for the electrons to get through this bulb. And as they're going through this bulb, they light up the bulb. Bottom line, the electrons that go through this bulb are the electrons that are right here. All right, they go through the bulb, and then they push everything back to neutral. But bottom line, you can think of it as kind of like water flowing through pipes. We'll talk more about that later. But the electrons move back home and neutralize everything, discharge it. But the light should flash on. Maybe you couldn't see it. I'll do it again. It flashed on and off. Hopefully it shows up on the video. It's not very bright. So I'm going to charge the capacitor again. It doesn't take very long, less than a second to usually charge it. All right, then I'm going to discharge. I'm going to allow the electrons to go back home. And once again, hopefully you can see the light come on just briefly. It's not very bright. These are used in like camera flashes. So what they do when you have a camera flash, they have a capacitor in there, and you have batteries that charge up the flash, because what capacitors can do is discharge very quickly and make a very bright flash. If you have the right light bulb and the right capacitor, you charge it up, and then it makes a huge bright flash very quickly, and then its discharge is done. You got to recharge it. But that's one place that they're used, in addition to other various functions in circuits, electronic circuits. So that's charging and discharging capacitor. All right, so now some of the technical definitions for capacitance. So here is the equation for capacitance. C equals Q over delta V, where delta V is electric potential difference. That's that fourth thing in that chart of the 4 main concepts in this unit. That is, we have electric force, by definition, well, by Coulomb's law, F equals KQQ over R squared. We've been doing those vector problems. Electric field, defined E equals F over Q, and E equals KQ over R squared. That's a vector. And then the energy, that's associated with point charges. Now we're going to have energy associated with plates. And we have to make a little bit of an adjustment here. The energy associated with point charges are scalars. It's U equals KQQ over R. And then the electric potential is V equals KQ over R. And then if you change your energy level per charge, change your potential, you get delta V. It's called voltage. In this case, like these batteries, each battery is 1.5 volts. That's the voltage. When you put two of them together in a row, they call that series, that's 3 volts. We'll talk about that later on. But here's the definition. This is just something that's made up. It's not really discovered. It's something that's made up for us. That's a true relationship, okay, that we define to help us then make devices that help us make electric circuits. But C equals Q over V, where C is capacitance. Q we already have. Q is in coulombs. Delta V is in volts. C equals capacitance. And we use the letter C for capacitance. So now we got another challenge because we also use C for coulombs. All right. So we got, in context now, this C means capacitance. Does not mean coulombs. Well, capacitance is measured in coulombs per volt. The units are coulombs per volt. So that's a little confusing. A coulomb per volt, we give a name. Coulomb per volt, we call that a farad. F-A-R-A-D. And we're going to use capital F for farad. So capacitors are measured in farads. We'll come back to that. All right. Let me move the screen down here. All right, let's talk more about this. Sorry about the delay here. All right, so yeah, so I guess I wrote that all down here. So so we also have simplified diagrams, what are called schematics. So this was the definition. This technically should have been delta V here. I cut and pasted that from someplace else. Sometimes we get a lot of times we get lazy and just put V there. But if you rearrange that, you get that equation, same equation. All right, and then what I did right up there a few seconds ago, capacitance is coulombs per volt, which we call a farad. All right, and once again, here's a somewhat simplified diagram, but the most simplified diagram is going to be something like this, where this symbol, it's a long, short, will represent batteries. This is common schematic diagrams when you are when we get involved in this, because we don't want to draw more complicated diagrams, we want to keep it simple. This line I'm drawing there is a wire, another wire. There's a couple different ways they draw capacitors, but the way in our homework is two parallel lines that are the same length. So these should be the same length. So that's a capacitor. So that represents the capacitor. This represents batteries, and we'll draw some more diagrams like that with multiple capacitors in the circuit. But without proving it right now, once again, the letter U stands for energy in joules, stored in the capacitors, 1/2 Q times, once again, that's delta V. So it's implied here in all these problems that all the V's in all these problems are all delta V. You really probably won't have a problem with that, so we'll practice that. So I've already mentioned that the dielectric is that piece of paper, the piece of paper you put in between the plates to keep them from touching each other so they don't short circuit. We have to have something there that doesn't let the electrons jump across, whether it's air or paper or whatever. But we're not going to do anything with dielectrics this year. We'll make mention of them next year and talk about those more so in AP physics. But this year, just make note there's something between there that helps keep the plates separated. It also helps contribute to the ability of the capacitor to store charge. So I already talked about, they look like little blue cans. They come in a lot of different sorts. There's also ones that are like little brown, flat, they're little brown rectangles. But there's also silver ones. But the most common thing is the blue can. All right. Those are capacitors. Oops, I got to erase all this. Right back here, let me move this. Oh yeah, so, let's go down here. This is a more complicated circuit where we have a battery and we have a whole bunch of capacitors. And we're going to practice a lot of these problems because we're going to have circuits that have capacitors by themselves, resistors by themselves, then capacitors and resistors. Then you start putting in other things like transistors, and we're not going to get quite that far, but this is entry-level, basic, and it doesn't look basic when you first do it. It looks complicated, but we're going to go in slowly here, hopefully, and then we'll practice, and I'll have more videos for practice to help you. But bottom line, this represents all these lines are wires. So we try to keep it so it looks neat, all right? Battery, and then like the one I just did there might just be a battery, then the capacitor, then another wire right here. But now I got a second capacitor before I get back to the battery. We'll talk about pathways here in a few minutes. And we also talk about the two basic types of circuits, which we'll get to, which you may have talked about maybe in 8th grade or whatever, series and parallel circuits, which we'll need a lot of practice on. But that is a more complicated diagram. We'll get back to that one. Let's move this page down. Okay, so a 12-volt battery is connected to a 20 microfarad capacitor. So once again, this is just simple, straight plug and chug. So if you just, that's the basic schematic diagram right there. You have a 12-volt battery. That's the potential difference. 20 microfarads. Micro is a common size of a capacitor. Micro, well, nano's even another, probably even more common. But how much charge is stored? Well, the basic equation is C equals Q over V, delta V. So we're looking for Q here. So Q is going to be equal to C, which is 20. I don't know why that's not coming out. It says 20. I'm going to move this over. C equals 20 micro. Micro is 10 to the negative 9th times delta V in this case, and delta V is 12. So I'm going to have the capacitance here is 20 times 12. So, well, 2 times 12 is 24. So that's 240. It's going to be 240 microcoulombs. I think if you do the math there, 12 times 20 is 240, and the micro is still there, or 240 times 10 to the negative 6, or it'd be 2.4 times 10 to the negative 4th. If you want to plug that all in, all would be equally valid answers. So that's the charge stored, and that's the charge stored at each plate. That's you can figure out how many electrons that is. If you divide that by the charge of the electron, that'll tell you how many electrons are moved from the positive plate to the negative plate. And each plate has that charge. The negative plate has a negative charge of that amount, and the positive plate has a positive charge of that amount because you took electrons off, so it has an excess of protons. So now the energy is stored. Once again, this is just plug and chug. The energy stored is 1/2 QV. And there's other equations once you start mixing and matching, so I had to think for myself. The energy stored is 1/2 QV. That's from the previous page. So if I plug in there, sorry, I'm just going to use some space over here. So the energy, potential energy, is kind of, well, this is plug and chug. 1/2 Q, which is 240 micro. So you got to remember to put the micro 10 to the negative 6th in there, times V, which is 12. So the energy stored in this one, basically it's 6 times 240. Don't have my calculator right here. Maybe I do. All right, so it's, well, 1/2 of 12 is 6 times, 6 times 240 times 10 to the negative 6. Well, it comes out to be 1.44 times 10 to the negative 3rd, which is milli, okay? I'll just put times 10 to the negative 3rd joules. That's how much energy is stored in that capacitor. 1.44 times 10 to the negative 3rd is 1.44 millijoules of energy stored in that capacitor.